Climate change is no longer a future threat, it is a present crisis. Global greenhouse gas emissions continue to rise despite decades of climate agreements and policies. Today, carbon credits are meant to be one of the world's most powerful tools to reduce emissions. They allow industries to offset pollution by investing in carbon reduction projects. A carbon offset is a way to balance out CO2 emissions by reducing or removing the same amount of greenhouse gases somewhere else. But today's carbon credit system is fundamentally broken. Markets are fragmented, opaque, prone to double counting, and fake credits. Verifications lack trust, intermediaries take heavy commissions, and high cost locks out small businesses. As a result, carbon markets have grown in size but not in impact. So, the challenge is clear. How do we create a transparent, trustworthy, and global carbon credit system that ensures every credit is real, traceable, and used only once?
Now, to fix the broken carbon credit system, we introduce a blockchain powered carbon credit ecosystem designed for trust, transparency, and real climate impact. Step 1, registration and identity management, that is smart contract 1 registry. The process begins with generators such as NGOs, environmental groups, and charitable trusts. They register on the platform by submitting their identity documents, project details, location, and land information. And now all of this information is securely stored in Smart Contract 1, the registry. The registry maintains unique project IDs, verifier IDs, geotag project locations, land area, and related metadata, IPFS document hashes along with timestamps. This creates a trusted on-chain identity for every project and participant, ensuring that only whitelisted and verified entities are allowed to enter the system.
Once registration is complete, validators submit MRV data including raw satellite imagery and geotech data collected via mobile applications and IoT devices. Since this data can be large, it is stored off-chain on IPFS while its cryptographic hash is recorded on the blockchain. This data is processed through a 4-stage multimodal pipeline to generate transparent and auditable carbon credits. In stage 1, we apply aerial semantic segmentation on high resolution drone imagery. Our model isolates vegetation pixels from non-vegetation, allowing us to compute the total restored land area in hectares. Stage 2 focuses on the multispectral biomass analysis using NDVI. By combining near infrared and red bands from zenithal 2 imagery, we calculate the above ground biomass. In stage 3, we predict 1 year incremental biomass growth using parameters such as temperature, humidity, soil pH, and salinity. Finally, in stage 4, the predicted biomass growth is converted into carbon and then CO2 equivalent.
The step 3 is verification, approval, and consensus. The protocol uses a stake-based validation mechanism to verify machine learning generated measurement reporting and verification data. Anyone can become a validator by staking 32 ETH, which grants a cryptographic certificate that provides validation rights. Block generators submit MRV input data along with a fixed registered ML model and the resulting output. Validators check whether the inputs follow defined guidelines, independently run the same ML model, and compare their results with an acceptable tolerance. Validators approve a block by signing it, effectively staking their certificate on the correctness of the computation. If a block is later found to break protocol rules, such as using invalid inputs or producing non-reproducible outputs, the approving validators are penalized by slashing their certificates worth 32 ETH, and the generator is informed of the rejection. This approach enables reliable and transparent verification of ML-based environmental data while aligning incentives for honest participation. The step 4 is carbon credit token minting. After successful verification, carbon credits are digitally tokenized. This is our smart contract 2. The verification smart contract automatically triggers the carbon token smart contract to mint ERC20 carbon tokens. Each token represents a verified amount of carbon absorption or emission reduction. These tokens can only be minted or burned through the verification contract, cannot be created arbitrarily, have a fully transparent on-chain history. This guarantees a clear and controlled carbon credit lifecycle.
Once minted, carbon tokens can be traded. This is step 5, trading via permissioned AMM automated market maker, a smart contract for. Industries act as consumers and purchase tokens to offset their emissions. Trading takes place on a decentralized exchange built using an automated market maker. This ensures peer to peer trading without intermediaries while still enforcing regulatory controls. Trading happens through an AMM where decentralized exchanges offer to make liquidity pools. NGOs and EGs can make their pools to trade their tokens with another currency. Industries can come and buy tokens according to the requirements. This involves no intermediaries and increase the level of trust. Prices are determined by the constant product algorithm x into y equal to k, which changes according to the supply and demand. When an industry wants to offset its emission, it retires carbon tokens. This is step 6, token retirement and carbon offset. This is done by burning the tokens on-chain, permanently removing them from circulation. Once burned, the offset is recorded immutably on the blockchain. The same carbon credit can never be reused, and the burn serves as proof of emission offset. This directly prevents double counting and double spending of carbon credits. Throughout the entire process, the blockchain acts as a single source of truth. It records registrations and identities, MRV data hashes, verification decisions, token minting, trading, and burning. This end-to-end blockchain-based system ensures that every carbon credit is verified, graded, and transparently managed, creating a trusted, auditable, and impactful mechanism for global carbon offsetting.